When it comes to implication, order matters. Okay. So now what I'm going to do is I'm going to extend this truth table. Okay. With a bunch of other formulae, with a bunch of other compound propositions that involve P and Q. And let's just play along for the moment. So, not Q implies not P. P, not P, or Q. Okay. So let's look at these two truth tables. Okay. So not P implies not Q would only be false when not Q is true and not P is false. So not Q is true when Q is false. So Q is false. Okay, and not P is false when P is true. So Q is false, P is true. So only in this situation is this implication false. Okay, so this is false. Everywhere else it's true. Okay, what about not P or Q? Okay, so not P or Q. Well, remember the or. It's only false in one situation where both of these are false. So Q must be false and not P must be false, which means P must be true. P must be true, Q must be false. Okay, so this is the only situation where the or is false. In all other situations, the or is true. Okay, now I'm going to ask you to compare. Okay, and I'll put a nice blue line here. Compare the implication with this, what's called the contrapositive of an implication, with this or. You will observe that whenever this is true, that's true. Whenever this is true, that's true. Whenever this is false, that's false. Whenever this is true, that's true. True, 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 true. False, false, false. So whatever the truth value of this is the same as the truth value of that. So these are equivalent. Remember, that's what equivalent meant. It meant that whatever the truth value, if P is true, Q must. If one thing is true, the other thing is true. If one thing is false, the other thing is false. So it's possible for compound statements to be equivalent. Okay, and we can evaluate the truth value of compound statements. Okay. Let's consider one more example, okay, which is Q implies P. Okay, so Q implies P. Okay, so P implies Q, Q implies P. Well, when is this false? It's false when the left-hand side is true and the right-hand side is false. So the left-hand side is true, the right-hand side is false. So it's only in this row that it's false. Okay, it's true, it's true, it's true. And you can see that if you take the and of this and this, so the and requires both to be true. So both are true here, both are true here, and in this case, one of them is false. So the and of this and this is exactly the truth table of equivalence. So equivalence is equivalent to the and of P implies Q and Q implies P. Okay, so that's a small side note. What's the big side note? Q implies P does not have the same truth table as P implies Q. See? True, 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 false, false, true. So when one is true, it's not necessarily the case that the other is true. When one is false, it's not necessarily the case the other is false. Okay. So P implies Q is not equivalent to Q implies P. The order matters. Okay. And that's very important. Okay. If I'm dead, then my eyes are closed. This is true. It's a true implication. If I'm dead, my eyes are closed. Okay. If my eyes are closed, then I'm dead. You see the difference? All I did is change the order. Very different statements. Okay. The order matters a lot when it comes to implication. So if my eyes are closed, please don't conclude I'm dead and bury me. Okay. Please don't conclude I'm dead and bury me. The order matters when it comes to implication. All right, let's consider an example, a slightly more complex example. So example. Okay. So let's define some statements. P. Okay. You are hungry. Q. You are thirsty. R. You visit the cafe. Or if you're in school, you visit the cafeteria. Okay. So if you're hungry or thirsty, so if, hungry or thirsty, then, you visit cafe. It's a reasonable implication. It's certainly plausible. We might think it's true. Okay, so let's just assume it's true. What this means is that this means that P or Q implies you visit the cafe R. That's now an even more complex compound statement. Okay, so let me ask some questions. Okay. You are thirsty. Okay, pop quiz. You are thirsty. Did you visit the cafe? Did you visit the cafe? These are the kinds of questions we used to get on the GRE analytical, or what are called logic questions. Okay. 1. 2. You did visit the cafe. Are you thirsty? Question. Answer it. Question 3. You did not visit the cafe. Are you hungry? Answer it. Okay. So now let's pause the video, answer these questions. I'll give you 2 seconds. So if you pause the video and answer these questions, you're an excellent answerer of logic questions. But what I want to show you is that we can use truth tables and the basic propositional sort of logic that we have defined here to answer these questions effortlessly. Okay, so you are thirsty. So what that says is P or Q is true because P is true. Because Q is true. Q is true. So P or Q is true. Since P or Q is true, okay, and this is a true implication, we know that true, you can infer R. So you can infer that you visited the cafe. Yes. Okay. You did not visit the cafe. So R is false. Okay, so R is false. Okay, so are you thirsty? So we know that if R is false, okay, it cannot be the case. So we know that when we have the right side of an implication is false, we can infer that the left side of the implication is false, because it's a true implication. So this is false. But when is the or false? When both are false. So this is false, so this must be false. Both must be false. So you are not thirsty, you are not hungry. So are you hungry? No. Oh, I was talking about this. Are you hungry? No. So you did not visit the cafe. You did visit the cafe. So R is true. Okay. When you did visit the cafe, R is true. So if R is true, well, in an implication, we studied this case. When R is true, you cannot conclude anything about this. This can be true or false. And since you cannot conclude anything about this, you cannot conclude anything about what's inside. So this can be true or false, which means P, are you thirsty, which means Q can be true or false. Okay, if Q is true, this is true. If Q is false, this could be either true or false, and you cannot infer anything. So don't know. There's an important difference there. We don't know. We know that Q must be true or false, but we don't know. So you did not visit the cafe. You did visit the cafe. You might have just been accompanying a friend. You may not be hungry or thirsty. So just because you visited the cafe doesn't mean you're hungry or thirsty. That's not contained in the implication. Okay. So work through this example, carefully on your own. It's a very important example, okay, to understand implications. I want to move on